Hello everybody, my name is Ahzi from Texas A&M, where I'm currently just joined Texas A&M in Qatar, and I'm only from the University of Strasbourg, but I have been working the last few years at Qatar Environment and Energy Research Institute, where this work has been conducted, and in collaboration with Shahzada Pamir Ali and Nicola Bart. And I would like also to thank Dr. Yusuf Zaz for inviting me for this presentation, which is on the multiphysics approaches and analysis for the prediction and performance of degradation and fatigue failure of PV panels. As you all know, there are certainly many advantages for solar energy, such as abundance, distributed almost evenly worldwide, and also less maintenance, some small scale and large scale possibilities. However, there are also disadvantages, such as the fact that we cannot harvest at night. The power production is greatly affected by the weather conditions, and I will talk about that particularly for desert conditions, because we are going to in this analysis I will be presenting, we are looking into the effect of desert conditions in terms of temperature and wind and so on. And of course, another disadvantage is commercial production and requirement for large areas. So the PV system performance can be decomposed into four actually parts, which is the part on the performance due to radiation and optical, and also the thermal performance, so which measured through the temperature of the cells, and the electrical performance, which in fact is measured through the maximum power of the PV cell or the module. And then also the structural performance. These PV modules, they will fatigue over time, and certainly they will degrade, their efficiency will degrade until they fail completely. So these are the three measures of performance, and I will talk about a few of these things. Actually, all of them. I will talk about the four parts in terms of modeling and simulation. Now, in terms of multiphysics modeling motivation, we wanted to, there are certainly a lot of models out there, but are not necessarily accurate, are not necessarily all physically based. There are a lot of simplifying assumptions, and may not be accounting for full transient situation. So we wanted to develop a model that is fully transient for temperature prediction, and also accurate enough, and that is coupled between radiation and optical modeling, thermal modeling, electrical modeling, and structural modeling. So that's why in each there is a different physics, and that's why we call it here multiphysics modeling. And also there is a strong coupling, as you can see in this chart in here. We have the radiation modeling, and we have the thermal modeling. Radiation model is connected to electric and connected thermal, and thermal is also connected to the structural modeling. So the motivation is for better visualization and assessment, to mitigate prediction error in each model, and to reduce computational time, and also to improve reliability and credibility of the simulations and predictions. So now, for the first part, this is radiation plus optical modeling. We proposed some time ago a simple model to compute the absorbed solar radiation, which is given by this relationship here, S, as a function of the global measured radiation, which is plane of array in this case, and of course weighed by these two parameters, which are the effective absorption of the PV cells and the average transmittance of the glass. And this is given in fact by the average transmittance of the glass is given by this relationship, which depends on the glass properties such as glass extinction coefficient, and also the glass thickness, and of course depends also on the incidence angle and transmittance angle, as shown in these in this picture in here. So this is a model that accounts for the global radiation throughout all the wavelengths, and this is different from certainly many models that exist in the literature. So the heat equation, this is thermal modeling, and for the thermal modeling we use the generalized heat equation, which is given by this relationship where rho is the density, C is specific heat, T is time, capital T is the temperature, K is thermal conductivity, and Q is internal heat generation. And these are the elements of the PV panel, the glass, the EVA, which is the polymer, PV cell, and the EVA again, front EVA, because these are the cells are encapsulated using the EVA, which is a polymer material, and also we have the Tedler or backsheet. In these first calculations, we are neglecting the anti-reflective coating. It's very thin. It's not going to change much the results. And in the first part, we are also neglecting the presence of interconnect ribbons, which are copper ribbons. But again, they are very thin, but we will come back to this. We are going to include them later on in a later phase for the degradation or mechanical degradation or fatigue degradation. Just to show you some of existing models out there. This is not exhaustive, but we're just listing some of them, and we're listing actually here the disadvantages of these models, and show also that the need for a more accurate and more inclusive and generalized model out there. Especially, it has to be the model that we would like to develop has to be fully transient, has to be simple, it has to be computationally feasible. So we worked on 1D finite difference model, one-dimensional. Then we extended it to a two-dimensional finite difference. We use also 2D finite element model, and we use 3D finite element. However, we focused mainly on, in this work, I will focus on the 2D finite difference and 2D finite element using ANSYS code, but he is using our code, which is we use MATLAB. But I will show also some results maybe from the 1D finite difference, just to give you an idea of how it does compare those results to how do they compare to 2D. And I will show also some 3D finite element, especially at the last part for structural analysis. Now, again, the continuity of the thermal modeling. So here I'm gonna look at the loads and boundary conditions. First, the heat generated, or internal heat, at the PV cells. So the internal heat generated the PV cell given by this relationship here, where S is the incident PV cell irradiance that we calculate from our proposed optical modeling. This is the area of the PV cell, and this is the volume PV cell. And eta is an important factor here. This is the efficiency, which in fact decreases with increase in temperature, as you see according to this linear relationship here. Okay, and then also the internal heat generation at the front glass, which is also given by this relationship, where we have the global irradiance measured, and we have the area of the panel or the glass and volume of the front glass, and this is the coefficient, which is the absorption coefficient of the glass. The other thing also is the heat transfer modes. We are using conduction, we are using considering convection, okay, free and forced and combined in one model, and then we are also of course using radiation, sky and ground radiations, as you can see from this schematic in here. Now, one thing we did to improve the accuracy of the modeling is to look at the heat dissipation and look at what's in the literature, and all of the existing models use this schematic here for the heat dissipation. Okay. And what we did is with this we were not able to accurately reproduce the experimental results. So we looked at how we can improve this, and by just looking into the boundary conditions, the sides and the top and the bottom of the PV panel, we decided to redefine these boundary conditions in terms of sink temperatures, as you can see here at the bottom, at the top, and also on the side. And by doing that, we were able to improve the results quite a bit. Here, one of the first results, these are the inputs from the measured data at the testing facility at QEERI, outside testing facility, where we measured the ambient temperature and incident POA. They are given here. This is the incident POA in blue, and this is the ambient temperature for 1 day. And this day was May, during May 2013. And this is the wind speed during that day. These are all measured. And these are inputs to our modeling. And then the output, we looked at, one of the output is look at the temperature at the back sheet. Predicted temperature in blue versus measured temperature at the back sheet in orange. And this is using classical dissipation modeling. The results are close, but not that great. Actually, as you can see from the root mean square error, it's 3 point something. Whereas here, when we introduced our new dissipation, heat dissipation modeling by changing or by correctly defining the heat sink, the sink temperatures on top, bottom, and sides of the PV panel, we improved drastically the simulated result. They are very, very close now to the experimental, with a root mean square of 0.8. We took different days with different conditions: a sunny day with clear sky, a sunny day with cloudy sky, a rainy day with overcast sky, and another two consecutive days, and to see how the model will perform. And in all of them, as you can see, the model performs really well if we compare the measured temperature at the back sheet against the predicted temperature by using our model. Now let's go to the 1D finite difference. We also looked at the 1D finite difference that we presented before at IRSEC, and we also improved the results by just changing the heat dissipation modeling, especially the top and bottom and side boundary conditions, or heat sinks, or sink temperatures, sorry. As you can see from this 1D finite element, again, these are the inputs from 1 day in July 2014 in terms of ambient temperature incident POA, and this is what we predict in terms of the temperature prediction. Another day, a sunny day with cloudy sky, a rainy day with overcast sky, and as you can see, the predictions compare really well in the 3 cases with the experimental results, which means that if we are just looking for temperature at the back sheet or even at the cell, one-dimensional model is sufficient. However, it all depends what you need. If you need to have an accurate distribution of temperature throughout the panel, in the 2-dimensional or in 3-dimensional, you have to go to 2-dimensional, 3-dimensional, and I will show you that 2-dimensional is probably enough. Okay, but 1-dimensional, it all depends on the application. If I'm just looking for temperature, 1-dimensional is more than enough. Now we also performed 2-dimensional and 3-dimensional finite element simulations. As you can see here, the first row is 2D finite element, and second row is 3D finite element, and in both we show the CAD model, and this is the NOCT, which is steady state analysis, but the transient analysis by taking 1 day during the by taking 1 day and simulating in Qatar and simulating the temperature of the back sheet, if the panel that is considered, we can see that we have very good accuracy with the root mean square of 0.8 and 0.6 in 2 dimension and in 3 dimension. So 3 dimension is a little bit more accurate, but not, we don't need to go there because it's computationally heavy and expensive, and I think the 2-dimensional is more than enough in this case. Now I go to electrical modeling, and the electrical modeling is used to estimate the maximum power. The inputs are the PV temperature or the cell temperature, and also the global irradiance. Now there are two ways of looking into this, either using simple power correlation, and there are plenty of models that exist there, or relationships proposed by different authors, or use a detailed electrical model that gives complete IV curve and calculate the maximum power, as you can see from the IV curves here. Now we decided to go this way, and we used before I go to what we did, just to show you how many correlation relations that exist in the literature actually to calculate the maximum power. Plenty. But is this good? Well, certainly it all depends on the application, it all depends on the type of PV that you are considering. In our case, by the way, probably did not mention it, we are using here the panel that we are considering is polysilicon based panel. So now the electrical model, we use the classical one diode circuit model, which is given by the current is given by the relationship here, and the parameters in red are the 5 unknown parameters, which are the light current IPH, or the diode dark saturation current, or series resistance, shunt resistance, ideality factor. So these are usually calculated through iterative methods or optimization techniques. All right. However, these are also dependent on temperature. All of these 5, and temperature of the cell, and also on the global irradiance. So to include the effect of temperature and irradiance on these, one can use an existing approach by De Soto and co-workers, where they propose the translation equations to give the photocurrent, for example, which depends on the irradiance and temperature, but the other parameters depends on only one, either temperature or irradiance, or constant, like here in the series resistance. Okay, so we developed a new idea based on methodology called the shift factor based method. Again, this is the one diode model as previously shown. The parameters 5, we call any parameter is called P, could be any of the 5 parameters, and the variables we have both the irradiance and the cell temperature, TPV here. In order to develop a generalized way for shifting these 5 parameters function of both the irradiance and temperature, we tried to fit the results from this one diode model to several IV curves for different irradiances, okay, and different temperatures. That's in this example from 25, 50, and 75, and here 200, 600, 800, and 1000 watt per meter square. And by fitting, then we were able to determine how each parameter will evolve with temperature, or with the irradiance by fixing temperature, or with the temperature by fixing the irradiance. And from this analysis, we were able to come up with this unified model that gives you any of the 5 properties here, how it will shift as a function of both temperature and irradiance. This is a very fully coupled model, and this is actually the first time that this type of modeling has been used in this area here. Now, if we look at the comparison between our proposed model and the De Soto method, we are comparing here the De Soto method to our model. As you can see, either for varying G and keeping the temperature constant, or varying temperature and keeping the G constant at 1000, in this case here 1000 watt per square meter, and here for temperature fixed at 25. So let's look at 25. I think the photocurrent, it seems to be following the same trend as de Soto, but not the others. They are completely different. But now if we keep the irradiance constant and varied temperature, again the photocurrent is almost the same as the de Soto, but the 4 other parameters are completely different. And let's just take these examples that are circled in red here. You can see that de Soto keeps the in both cases, I mean varying temperature, varying irradiance. The shunt temperature, the series temperature, sorry, is constant, okay, by de Soto, but it varies drastically by our model, which is physically sound actually. Now, if we look at the comparison of our model to de Soto for the IV curves for different irradiances, okay, you can see here that our model predicts very well the IV curves for all ranges of irradiances. De Soto works well for 1000, close enough for 800, but it deviates completely for others because it was fit to these two only in ours. By using a few, you fit, and then you can predict very well throughout all ranges of irradiance and all ranges of temperature. And now the last part, which is the structural modeling. In here we are interested in estimating the lifespan of the PV panel. Of course, the loads that are used for this are various. The wind, for example, mechanical load, wind, snow, and weight. The thermal load is extremely important, and actually we're going to focus in our work on thermal load. Okay, there are also radiation loads, which also degrades the UV, and there are chemical loads that just add moisture and heat speed up corrosion. So we are not considering corrosion or radiation degradation or mechanical load degradation. We are considering only thermal. Okay. By the way, we are interested in looking into one part of the PV panel that would fail. If you look at this chart here, you can see that most of the failure comes either from corrosion or from the breakage of the copper interconnect, which is 41% corrosion. So we are focusing here on the interconnect. So we are going to see how the failure can come from the interconnect. And you can see on this small picture here the interconnect in the red between the cells, green cells. Okay. So for this, one can use a fully three-dimensional finite element, which is very expensive actually computationally, but we reduce this by looking into a method that we proposed recently, and that is called an approach that is based on 2 steps: 2D global simulations and 3D fully 3D simulations once we know where the higher stresses are. So let's go back to here. We used one string only rather than the entire panel, and we simulated this one string for 2D simulations, and from that we were able to see where the maximum stresses or maximum deflection actually occur. If you look at here is the interconnect between 2 cells, okay, and it does occur in this central here part, which is not surprising. Okay, so we know that the higher stresses or deformation are here, so we focused on this and we used 3D finite element simulations to calculate stresses and strains and so on, as you can see from this three-dimensional finite element mesh. For this, we need to define the constitutive laws for each of the elements of the PV panel. So obviously the silicon was taken as linearly elastic, the glass as well. The CTEs of silicon is varies with temperature. As you can see, the variation, we included it. The CTEs of the copper vary also with temperature, and we did include this variation. And the EVA, which is a polymer, it's a viscoelastic material, and we took also the the effect of temperature on this, and we adopted a viscoelastic model. For the copper interconnect, which is of great interest to us here to see how it fails, we took an elastic plastic model. So we have elasticity, then we get to the yield or beginning of plasticity, and the material plastifies with hardening, and this is kinematic hardening, which is widely used and a must actually for analyzing fatigue. Okay, now the other thing we did is, since we are focusing on this copper interconnect and central part, we wanted to know what are the initial conditions actually that comes from the processing or the making of the panel, and that is the lamination process. So lamination process consists globally of heating and then cooling to 150 degrees and then cooling. But when you cool, well, you have developed thermal stresses, and you can see that the thermal stresses are really high, 158 megapascals, whereas the yield of the copper, the yield point is only 90. It is written here, I think. It's only 94 megapascal. It's not written here, but anyway, that means that during the lamination process, the interconnect had, especially in this central part here, did undergo plastic deformation. Now, in order to simulate fatigue, because we have cyclic loading, every day you heat and then at night you cool and so on, this is cyclic load. So if you apply a cyclic loading, which in terms of temperature, well, you will get a plastic deformation, which is also cyclic, and the amplitude of the cycle is given by delta epsilon plastic. And this amplitude of the plastic deformation is related to the number of cycles to failure by using a model called Coffin-Manson model for fatigue and fatigue for ductile materials. Okay, this fatigue model involves two parameters, which are the fatigue ductility and fatigue ductility exponent, which we got from the literature. They were measured experimentally by different authors for copper. And now, how to simulate this cyclic thermal loading? Well, we chose one day, and then we repeated it many times to have a cyclic loading. So day, night, and so on. And you can see it from here. This is, we choose one day in June, but we also choose one day in January. So two extreme cases in Doha. And this is what we measure in terms of, or calculate also in terms of temperature during this day of the panel in the cells. And this is for January. This is for June. And these are the stresses during the same day. The stress, how it goes, it does relax because temperature increases, then it decreases and so on. That's why you see this relaxation, because of temperature increase. And the same thing here for this other day, okay, which is in January. Again, you see the evolution of stress from the same day. What we did, we took this situation and we repeated it 25 times, okay? And then we measured so 25 days, in fact. So we measured the plastic deformation, and as you can see, it is cyclic, and the amplitude becomes smaller and stabilizes. And it is when established in fatigue modeling that you have to go beyond 20 to at least 20 cycles to stabilize the amplitude of plastic strain to use the fatigue model that I showed before. And it stabilizes after, in our case, even before 20 days or 20 cycles. So now, by using that model, as you can see from here in this table, if you can concentrate here, the fatigue cycles, the number of fatigues is given by 7,904 for July, I think they are actually mixed up here. This is for January, 4,070, and this should be for June, 7,000. But if you convert this into years, so this is wrong. This is the wrong way. Okay, this should be June and this should be January. But if you convert to years, this is correct. 21 years for January and 11 years only for June. And if you compare to the manufacturer, actually lifetime given by the manufacturer is 25 years PV panels which are based on silicon or polysilicon, where here if you take the average between the two is only 16. So it is not surprising. We are in a desert area, the harsh conditions in terms of temperatures, and that's why we found less in terms of lifetime. And this is very important for designers to know about this, designers of PV panels. So now, in conclusion, so we have developed a radiation plus optical model in a unified way and simple. We have also developed a thermal model or improved thermal model, one-dimensional, two-dimensional, an electrical model, and we proposed a novel concept for shift factors to capture the effect of temperature and radiance on the parameters of one diode model. And we have developed a structural model based on 2D global modeling and then 3D local modeling to predict the lifespan of PV panels, and we found that it is much less than the 25 years given by manufacturer when you are in areas like in Qatar or any desert, any equivalent desert areas. So overall, we have developed unified sample approaches. We increased accuracy of the prediction of the modeling, and we also reduced drastically the computational time. And with this, I would like to thank you, and I'll be ready to any questions from the audience. Thanks a lot.